Okay, it's 10 past 10 in Paris, and it's sunny and shiny. It's 10 past 5 in Singapore, and I guess it's always sunny and shiny because here in Paris, again, we have to remark whenever there's the sun in November. And it's my great pleasure to resume the computational materials chemistry session with my great friend Rodolphe Vuilleumier. And not only, of course, he's a very distinguished professor at École Normale Supérieure and Sorbonne Université of chemistry, but also is with Rodolphe that we started in more than 5 years ago with the PISA CMS, the Paris Advanced Computational Material Science School. So it was in 2015 when we organized it for the first time. It was supposed to be one shot. And it went so well, and we had so much fun, the two of us, and also many of the other colleagues that you saw these 3 days, that we decided that it was worth doing that every year and to export it around the world, Bangalore, Singapore, other places. So that's it's really a great pleasure, and it's a great pleasure to see that to have him today speaking about solvation in reactive environments, from CO2 capture in molten carbonates to versatile charging of graphene in water. So please, Rodolphe, stage is yours.
Yes, thank you very much, Marco. So indeed, let's hope that we will be able to resume this PISA CMS series of schools next year. It's always enjoyable to these schools. In the meantime, we'd like really to thank you for putting this workshop online this year. It's been really interesting these 2-3 days, not only the talks, but also the discussions. So thank you for the opportunity to show some of our results. What I would like to talk to you about is first some application of first principle molecular dynamics. And some point I would like to discuss also some of the limitations, what we do to go over these limitations, mainly time scales and length scales. Fabio has shown some of these. The type of chemical reactions I would like to address in these two examples are very different from the type Fabio addressed in his talk. What I would like to describe our system where actually, in a sense, the chemical reactions are quite fast and quite numerous, but the quantity that we want to extract from them, like transport coefficients, equation of states, still need a lot of sampling. So indeed, what we are interested in, chemical reactions, in condensed phase in an environment, we will see that the two examples I would give actually have a strong participation of the solvent in the chemical reactions. And for this first principle molecular dynamics, simulations are ideally suited. The idea is that we run molecular dynamics simulations, so you sample the phase space, but these are called first principles because the forces on the atoms are obtained from density functional theory calculation of the electronic state. So it's well suited for these chemical reactions or any other system where the electronic state is strongly coupled to the atomic motion, hydrogen bonds, even formation of complex, polarizations, etc. And as Marco also described yesterday, first principle MD and the explicit treatment of electronic state allows for many things in direct comparison with some experiment like spectroscopy. We've also heard Ari, and we use it for identification of species, structure, looking at the chemical bonds that are formed. But the thing that we want to do here, I won't talk much about spectroscopy, which is another of my topics, vibrational spectroscopy in particular. But the one thing I would like to show is transport mechanisms and transport coefficients when reactions are involved, and thermodynamics. And these mean that first principle MD we have some shortcoming in terms of how long, how large we can sample the system. And I will show you in these two examples what we did. First one will be to looking at carbon dioxide in molten carbonates. I will introduce that in a minute. And the second one is indeed the adsorption of ion of hydroxide and the charging of graphene, and the comparison with boron nitride in its hexagonal phase, which is isoelectronic. But first, why molten carbonates and CO2? Of course, that we've heard a lot about, but why molten carbonates? We were first interested in this because this is another use of first principle MD, is really to look at system at extreme condition, high pressure, high temperature. And we started a collaboration with geochemists, and they were interested in particular, they showed that they were in the mantle regions where most of the liquid is actually not full of silicates, but has actually a high carbon content. Even so, the mantle itself has a very low carbon content. The liquids that are formed in some places in the mantle are very rich in carbon. And these, compared to silicates, they are much less viscous. And so they play a crucial role in the differentiation in the transport in the mantle. For example, they've shown to show very high electric conductivity, which silicate doesn't have. And this is how they could actually detect, through magnetotelluric experiments, they could actually detect the presence of this carbon-rich liquid inside the mantle and about 300 kilometers deep. In simulation, silicates have been very much studied. There were very small information actually on the carbonates themselves, which apart from this geologic application, they also have some technological application in the molten carbonate fuel cells. So because of their high conductivity and actually rather low for molten salt, rather low fusion temperature, about 600, you can go down to 550 degrees Celsius. Then they can be used as the electrolyte for fuel cells. And in particular, they also have a much larger solubility of CO2 with respect to other molten salts. Here I show a fuel cell. You see, it's not the type of fuel cell that you would put in a car or even a bus. This typically is the fuel cells that you use to power a small town or a hospital or a big facility. These are working. You see this one is the photograph of a commercial one. There are two companies in the States or in South Korea that produce these molten carbonate fuel cells. One of the things that we are trying to do at the moment, and this is why we'll be interested in CO2 in these carbonate fuel cells, is to reverse the process and actually being able to sequester CO2 and to reduce CO2 in some usable fuel rather than produce electricity. We would like to reverse the way these fuel cells work to make them molten carbon electrolytic cells to reduce CO2. An example, I say these molten carbonates, they are very low viscosity compared to silicates. They have very high electric conductivity. And today, there is only one volcano that emits molten carbonates. Most of them, the lava is molten silicates. And this gives you an example of the very low viscosity of this material, which is about the viscosity of olive oil. Is a movie of this carbonate lava emitted by this volcano in Tanzania. And as you see, this has nothing to do with the typical lavas that we see from silicates. This is, again, about the viscosity of olive oil. And the temperature, you see how the picture where the movie was shot, you can approach from not very far because the temperature is about 500 degrees lower than typical silicates because the fusion temperature is also lower. So we started, and we go very short on this, on the simulation of this pure molten carbonates with first principle molecular dynamics simulations. And we were interested for the geochemists, but also for these applications into the determination of the equation of states, transport properties like electric conductivity and the viscosity for a bunch of systems, from the one that are interested for geologists, magnesium carbonate, calcium carbonate, to the one that are interested for these applications, which are more alkali carbonate, lithium, potassium, sodium carbonates. The thing is that for determining equation of states, the transport coefficient like viscosity, we can do that because we are in a good situation with molten carbonates, because they are very low viscosity, very high diffusion coefficients. We can do that for few phase points in temperature and pressure, but we cannot compute with first principle MD a full map of pressure, viscosity as a function of temperature and density for determining a full equation of states. So the path that we did was to construct an analytical force field, a simple one with partial charges, repulsion, dispersion. You see partial charges and a simple exponential repulsion and dispersion attraction, which was fitted on the first principle MD results. Of course, this is a typical step that you do in this situation. This is where, at the moment, there is a lot of work to indeed try to replace what we did there by a artificial intelligence machine learning techniques. This is still at the verge of what these techniques can do, because we have many species in the system, not only carbon and oxygen, but also if we go to alkali, we have lithium, potassium, magnesium, calcium, and there are too many species for the current state of the art machine learning. But this is certainly the way to go, is to, as we have addressed before in the workshop, to go from first principle MD to larger scales by a force field. And with this, we could compute indeed the viscosity as a function of temperature. So on this axis in Kelvin, and as a function of pressure in gigapascal. And the comparison, so a map is the blue one, and the experimental one is the brown one. We have too large dependence on pressure, but we have in the right range of viscosities, which is quite nice. It's very seldom in this type of applications. We could also compute the equation of states and describe the stability region of molten calcium carbonate with respect to the two crystalline phase, calcite and aragonite. And here's an example of a geological application where we could look here at the melting curve of calcite as a bunch of material will go up in the Earth's mantle, and at some point the calcite will melt, and if the mantle is hot enough, then it can reach the surface. And what we can see is that the current adiabatic isotherm is such that seldomly we'll have some carbonates that can reach the surface, except in some hotspot. This is the one in Hawaii, but the Tanzania is one hotspot of the same kind. And what we see that in the Archean mantle, which was much hotter, then indeed the molten carbonate could reach surface, and there are many traces of that, especially the Yellowstone Park is a manifestation of carbonates that has reached surface on a large scale. But what we like to address is CO2 in this system. So we see this system also is like CaO with stoichiometric CO2. We can still put more CO2 in it. And here's a movie from the F principle MD, and we see that it reacts with the carbonate itself, and we've seen here a reaction of CO2 with carbonate to form another CO2 with the carbonate and even a carbonate behind. Now, if I go much further, maybe somewhere here, sorry, what we see is that we will have transport of CO2 actually through a series of these reaction of exchange with a neighboring carbonate. So in up, we see that we have in purple some kind of a reaction intermediate, and then we have transport of the yellow CO2 quite far in the cell, while we have little displacement of the atoms. It actually diffuses through these ups. So we are in a situation where we have many of these chemical reactions that are quite fast in a sense, so we can sample them. And what we saw in the meantime is that there is formation of an intermediate of another species, pyrocarbonate C2O5 2-, and which is reminiscent of H5O2 plus that Michele talked about on Monday for the diffusion of proton in water. There's lifetime of the order of picosecond, depending on the system we are considering, alkaline earth carbonate or alkali carbonate. And it diffuses through a kind of Grotius mechanism. It's like we have the acid CO2 in the base, like we have H3O plus in the base H2O, and it diffuses through an oxogrotius mechanism. The O2, the CO2, there's an O2 minus transfer to CO2, forming this intermediate reminiscent of H5O2 plus in water, and then the transfer is complete and we have a new CO2 that is formed, and the diffusion of CO2 goes through these ups of O2 minus. We could check that these are indeed ups of O2 minus, and is here I put the in pink are the Vuilleumier orbitals that represent the doublets, electron pairs in the system. You have 4 of them around each oxygen, and when the oxygen transfers, it actually transfers with these 8 doublets, so that 4 doublets, so 8 electrons. So indeed, this is an O2 minus that transfers, and there is no independent transfer of Vuilleumier orbitals. They actually move along with the oxygen, stick to the oxygen, so it's really an O2 minus transfer. We could not really compute still the diffusion coefficient. It's would need much larger simulations. Somehow it would be some waste of time. We could look at the statistic of the ops, and from the statistics of the ops, then you can build a model for the diffusion coefficient that we estimate to be about 3 times the diffusion coefficient of carbonate ions themselves. So this remains to be seen experimentally. We're trying to work on injecting carbon-13 in carbonates in order to look at the diffusion of carbon-13 and the exchange with carbon-12. But at the moment, this is not a quantity that is experimentally available that may be interesting when we want to look at CO2 reduction in electrolyte cells using these molten carbonates. Very quickly, it has a role on solubility that we try to address, and this is the ongoing work at the moment to try to look at the solubility of CO2 in different environments, dependent on the position, on the composition, since this is how we'd like to make better fuel cells or better electrolytic cells, I should say. I will skip that to go to the second part, second application. And the adsorption of hydroxide on graphene and HBN. There I relate to experiments that were conducted by Lideric Bocquet, who showed that again at the nanoscale, we've heard some of these experiments by Laura this morning, and more later with Mathieu. The experiment at this nanoscale, he looked at the transport of current through nanotubes of BN or graphene, and it showed, Lideric showed that there was quite large surface charges, especially on the boron nitride, that can reach up to 1 coulomb per square meter. So very, we call it giant charges. And with a simple equilibration model, it relates to a surface pKa of about 5.5. So the adsorption, very strong adsorption of OH minus on these surfaces. This may have applications, for example, in blue energy, using here another phenomenon than the one that Laura alluded to. Here they wanted to use it for osmotic energy. That is to, indeed, when you have like salted water and water with a lower concentration of salts, and then you use the gradient of concentration to produce an electric current if you have surface charged, which where the difference of concentration induces a difference in Debye length on the both sides, which introduce a gradient of pressure in this surface region that induces then a current, and because the system is charged, it induces an electric current that you can try to get for making the get electricity from this gradient of concentration. So you need surface charges, and we wanted to look at what is this hypothesis of hydroxide being adsorbed on this system correct? We first did DFT calculation on the isolated surface with an isolated OH minus. We did some of things that we Fabio alluded to in the previous discussion, answering the question of Igor, that we went from the 0 Kelvin energy calculation to an estimation of the free energies, and we could get a pKa for Bn, which is exactly in the range that was obtained experimentally, while graphene has behaved completely differently with much larger pKa. That qualitatively, this is the order that you wanted to obtain, but graphene is much too large. Experimentally, we would like to have something that graphene will be around pKa of 9 or 10, and this is much too large with respect to the experiments that were conducted by Lideric Bocquet. So what is missing is probably the solvent. Perfect. Thank you, Marco. So we introduce the solvent explicitly using, again, a first principle MD simulation here for Bn, but we did it also for graphene with an extra hydroxide in the cell. And we did, in this case, umbrella sampling simulation that Fabio described earlier, to compute the free energy profile of this system as a function of distance between the OH minus and the surface. Very close to the surface, in the chemisorbed region, we see that indeed Bn can chemisorb OH minus, which graphene cannot do. However, we discovered that there was a well a little bit further away, about 3 angstroms, some kind of physisorbed region where OH minus actually has a minimum of free energy and can stay close to the surface without forming a chemical bond with the surface. And you see, this is this type of simulation of situations, and it's really the way that the surface, the water molecules form hydrogen bonds, and the way OH minus is solvated in this region that favors slightly the presence of hydroxide in this region. You can also look at the movie, and if you have hydroxide in this region, it stays there for about 10 picoseconds this movie. And we see that it's still ops, because OH minus can have proton ops with O2 minus in the vicinity. And but we don't have diffusion in the bulk. The OH minus is trapped in the surface region. And we could look at these ops while so there's a Grotius mechanism again, but on the surface now, because the OH minus is still trapped on the surface. What goes on is that during the ops, there is a switch of angles between 0 and 190 degrees with respect to the surface, such that when actually the system goes higher, it cannot diffuse away because it doesn't have the right orientation to do further ops toward the bulk. The only ops that it can do is to go backwards closer to the surface. So it oscillates between two positions close to the surface. And so we have transport of OH minus also on the surface. We don't not only have creation of charges on the surface, but we have also transport of OH minus on the surface, so a surface current. And when we try to reassess the experiments which were not measuring directly the surface charge, but which were measuring the conductance of the nanotube as a function of pH, for example, what we need there is, again, the first principle MD is at its limit, because we model here only one OH minus if there is adsorption of a few OH minus to large surface charges around Coulomb per square meter. Then there is electrostatic interactions between the OH minus. You have formation of a double layer. We don't have any counterion in the simulation. And so we need to put all this. This will be much too large, again, to put in a full first principle MD simulation that contains all the ingredients, enough counterions to describe the double layer, etc. So we need to use for that all the techniques, and we've simply used theoretical models describing a Poisson-Boltzmann description of the potential at the surface, and then the chemical potential on the surface depend on the Poisson-Boltzmann induced electrostatic potential at the surface. And we've also used a model for the conductance as a function of the surface charge, to which, however, with respect to the typical model, we've added this extra ingredient that the charge is not fixed on the surface, but can diffuse and can be a conductivity, a surface conductivity at the surface. And in particular, this second term is very important to reproduce experiments. So the circles are experiments, so measurements of conductance, not of surface change anymore. And the dotted lines are the result if we fix the OH minus, if we neglect the diffusion on the surface, and the straight lines, the full lines are the results of our model by putting the free energies that we compute, and by putting the an estimation of the diffusion coefficient of OH minus on the surface. And you see that we fit very well with experiments, much better than if we neglect the conductance. So this calls for a reinterpretation of experiments, because it means that the surface charges, which were also extracted from ionic conductance from this analytical model, should be corrected to get more precise surface charges. With this, I will just conclude here some summary of these two examples. I just wanted to illustrate another situation then where FPMD is important, is when you have quite fast chemical reactions where really involvement of the environment is really participating through this oxoglottis or the glottis mechanism for the diffusion of OH minus. And in that case, FPMD, you have to do some scale up if you want to really have things like equation of state, transport coefficients. And we use force fitting. Of course, machine learning will be the next thing to do. Yeah, some acknowledgements, and let me thank you for your attention.
Okay, thank you very much, Rodolphe. Great talk. So are there questions from the audience?
I have one.
Go ahead, Christian.
About the carbonates, okay. In a way, I mean, this process of attachment and detachment because of these chemical reactions, somehow, I mean, reminds me of Levy flights. Okay, of course, I mean, in your model, you get diffusion because we have a diffusion coefficient, but I was wondering whether you could have a regime of a Levy flight or something like that.
We didn't see any, and we didn't see any fractional diffusion coefficient. But we don't have the statistics to look at that. We did much larger simulations with an empirical force field that I had designed for proton diffusion in water, and we didn't see any of these Levy flights. It's after some length scale, we end up with normal diffusion, no fractional diffusion. Yeah.
Okay.
Yeah, too bad. This one would be nice. And the surface, it should be different. Huh? We don't have the statistics at the moment for the surface. No, the surface can be different. At 2D, yeah, this can be very different. Mm.
Other questions from the audience or the chat or vocally? My question is related, Rodolphe. Of course, I think I know your answer, but still, I think it's useful to say once again. Yes, that I mean, you mentioned better force field or better machine learning. I mean, do you think what's your perception about how this will how and if and how this will dramatically change the predictive power of our kind of calculations, where you have an ideal surface rather than a real nanotube with no defects, or if you have one defect, it is so important that since the size of our simulation cells is small. So, I mean, all this stuff, in the end, I mentioned yesterday that machine learning can help us in overcoming some of the obstacles. But yes, my feeling is not it will not be the magical wand. And so, what's your feeling about that?
Indeed, there's this scale up, and we've seen Lara, etc. If you want to go and include all these the contourings, this is one way. The other thing is that here everybody is polite. So there's no discussion about the usage of DFT in these settings. But we've had talks about highly correlated systems, and I'm sure they're very polite of not telling us what they're thinking about density functional theory. And I think that one thing that we always claim is that we need to have a kind of balance between sampling, computer time, and the quality of the electronic structure calculation. And I think this will move. That is, we will not be able to, we should spend now much more time, and we are, for example, moving to a hybrid density functional theory. This is the first step, or some people are already moving to MP2 simulations, and then you learn the force field on the MP2 electronic state calculation. But the kind of trade-off that we claim to use DFT is not true anymore. We should do much less electronic structure calculations, because most of them will be replaced by the force field that is created on the fly. And whenever we encounter a situation that has not been learned, that has not been trained, then we need to redo a few electronic states calculations, but then we should go for the high level one and not use the low level. I mean, GGA is not bad, but we should go to better than GGA.
So that's good for the audience also, because I mentioned yesterday the historical separation between physicists and chemists. So we see that Rodolphe rightfully claims as a chemist that we, the physicists, usually tend to settle easily on DFT, because yes, DFT today is still the best compromise between accuracy and calculation length when you do everything fully ab initio. And that's something we unavoidable today. But the spirit where I mean, once something that I didn't have time to mention yesterday, just briefly. Once the separation was between people doing classical calculations with model interactions and ab initio calculations. Now. And then it was, of course, within the ab initio, the DFT, mostly physicists, the quantum chemistry, mostly chemists. Nowadays, problems that we have the ambition to treat by computational methods are so complex, so multi-scale, then all these historical separation are falling down little by little, and we are just going to already calculation frameworks. So the level of theory can be changed or should be changed on the fly, as precisely as Rodolphe said. Then at some point we should add some more refined models as the ones that Fabio and Laura presented earlier. So all of this, at some point, probably in 10 or 15 years from now, will be totally routine and will be computational tools will be great to do a lot of things on different scales and different scales of time and length. Nowadays, it's still a work in progress. That's my feeling about all of this. Okay, if there are no other questions, I would thank Rodolphe again. And I will call for the final talk of the morning, and so final talk of the workshop, which will be given by Mathieu Salanne. I see Mathieu with flowers behind or something of the like. Okay, so thank you for sharing your screen. So as I forgot to tell everybody else, so it will be the only one to hear that I will tell you when you are 20 minutes through that you have 5 minutes left. So don't be surprised if I jump in your talk.
I should be on time.
And so Mathieu is a little introduction before. Sorry, Mathieu. I mean, we know also well each other also well in this community that I almost forget that I still need to introduce people. So Mathieu is a professor here at Sorbonne University, a chemistry professor in the Phoenix lab, and so he's somebody who's in Institut Universitaire de France. He got an ERC, so he's one of the most prominent researcher in our community here in Sorbonne, and so he's also part of the PISA Paris Advanced Computational Material Science School since 2015. He's also part of the Maestro Consortium, and so he's our battery guy. To make it a bit short, but he's our Sorbonne big, and not only Sorbonne, big expert in batteries, capacitors, supercapacitors. So today we're gonna talk to us about efficient storage mechanism for building better supercapacitors. So, thank you, Mathieu.
Thank you, Marco. So today, I will talk about mostly one application about electricity storage. So let's start with a very usual slide about energy storage. So you all know now that the energy transition is a very important topic in science and in society in general. And I think there are 3 levels at which we are now using electricity storage devices. The first one is very well implemented. It's about portable devices, so laptops, cell phones, and so on. The second step is now under deployment with a huge increase of the use of electric cars all over the world. And the last step will be the electricity storage from renewable sources. And well, this part, for the moment, I'm not sure that we will really be able to target this. But for sure, the electric cars is very important at the moment. And so, in fact, the most important device there are lithium-ion batteries, but there are also some other things that can be helpful. And in fact, a good way to look at the energy storage on a map is by looking at such wagon plots in which you have the specific power versus the specific energy, because we always look at energy, but in fact, power is also a very important component as soon as we look at electricity. And so, in fact, on this map, you see that on the top left, you have conventional capacitors, so small amount of energy, but high power. On the right and bottom, you have lithium-ion, a lot of energy, but small power. And supercapacitors that I will talk about today are intermediate because they have good specific power, good specific energy. And in fact, the good way to look at this is to make a sport comparison. In fact, the lithium-ion batteries are marathonian, so they allow to go to very long distances, but then they take a long time to charge. And also you will not be able to do lots of marathons every year. You can do 2 or 3 if you are a professional. But supercapacitors are more sprinters. So in fact, they allow you to reach high power, high speed, but you cannot, of course, run at the same pace on a long distance. And then the advantage of capacitors, the same as for sprinters, is that you can do a lot of races. So you can charge and discharge them very often, millions of times compared to batteries. So in fact, the capacitors are used, for example, in a stop and start system in cars, and they are more and more widespread in a lot of applications where we need large power instead of large energy densities. So how do these devices work? In fact, they are much simpler than batteries because everything is based on physical adsorption. So you have 2 electrodes, which are porous. So here you have porous carbon, which is the most used material. And in fact, when you apply a voltage between the 2 electrodes, you start to accumulate ions from the electrolyte on the 2 sides. So you will enrich in cations on one side and anions in the other side. And all the energy is stored at the electrolyte interface in the region that we call the double layer. And so there are 3 quantities which are important. The voltage of the device, U here in the energy and the power density, the capacitance, which is an interfacial quantity, and the resistivity, which is mostly linked to the conductivity of the electrolyte, so it's quite easy to tune. So in fact, the most important thing on which people try to work is increasing the capacitance, which is the interfacial quantity. But in fact, this quantity depends on a lot of parameters. So you can change the electrode surface area, you can change the size of the ions, you can change also the nature of the solvent, you can change the concentration, you can change the porous network structure, because carbon, you can synthesize billions of carbons with different structures. So you are in a very large parameter space, and so there was no real systematic study until something like 10 years ago, I would say. One problem for theory is that we are dealing with concentrated electrolytes. And in fact, the main theory that was used and still used is the Guy-Chapman's term that tells you that you have a strongly adsorbed layer and then a diffuse layer. But in fact, this theory works only up to concentration of 10 to the power minus 3 mole per liter. And this picture that we always use is wrong because, in fact, such concentration corresponds to 1 ion pair every 100 of thousands of water molecules. As soon as you increase the concentration, it doesn't work anymore because you have strong correlation between the ions, they attract each other, and so you cannot use this picture in principle. And so this was more or less known since a long time, but it was more formulated in 2007 by Kornishev, who showed that you need to account for several effects at high concentration in analytical models. And then there were the first simulations by Ruth Lindenbell in Cambridge, who showed that you have very strong cation and anion interaction at the surface in ionic liquids. And so this service cannot be used anymore. So the second point is that we also, on top of using concentrated electrolytes, we have nanoporous systems. And so the main experimental results obtained in 2006 by the groups of Gogotsi and Simon were by using carbons in which they were able to tune the porosity by playing on this reaction here, starting from titanium carbide and chlorinating. You end up with titanium tetrachloride, which is evaporating, and you end up with a nanoporous carbon. And depending on the temperature at which the synthesis occurs, between 1000 degrees and 400 degrees Celsius, you have a porosity that is centered around 1 nanometer, or even you can go down to 7 angstrom. And by using this kind of very microporous carbon, they show that the capacitance can change by a factor 2. So this is a very large difference. And in fact, you have very strong confinement effects in these devices. So we have 2 important effects to take into account. It's large concentration of ions and the nanoporosity of the device. And then, of course, in simulation, we have another issue, is that we are treating a system which has two sides. On the one hand, you have a metal, so in which the charge carriers are electrons, and on the other side, you have a liquid in which the charge is carried by ions. And in general, when we want to study metals, we use quantum mechanics. When we study ionic solutions, we have to resort to classical simulations because of the sampling issues that Rodolphe was mentioning just before. And so we need to have a model that is able to tackle these two. And our approach is based on the work by Sprick. We propose the model in which the charges inside the metal are fluctuating in order to have a constant potential all over the material. And so this was discussed mostly by Laura this morning, so I will not go into further details. But here you have the link towards our molecular dynamics code that we use for such simulations. So today I will talk to you about some systems we've simulated since 8 years now, I think. So we started with planar graphite, and this is a kind of model for us that allows us to have some reference results. So it's a good planar surface. And then we did two types of nanoporous systems. First, the carbide carbon that I've just shown you. And more recently, we studied nanoporous graphene because it was widely investigated in experiments. Concerning the liquids, we're using highly concentrated electrolytes, as I said. And so we go from the pure ionic liquid, in which you have no solvent, towards systems in which you have a ratio of 1 ion pair for 10 solvent molecules at the maximum of solvent. So this is now changing because our code is more efficient, but all the results I will show you are based on older results, in which we had to simplify a bit the liquid because otherwise the simulations were too long. So we used some coarse-grained models, which means that instead of having all the atoms, we were, for example, representing the anion, the PF6 anion, with only one sphere. So this is a simplified representation, but we used force fields that allowed to represent very well most of the physical quantities that are known for this liquid. So even if it's not atomically accurate, it's at least accurate for transport and thermodynamics. And so here you have an example of the first simulations we were doing, so more than 5 years ago, where we apply a voltage between the two electrodes, and you see, well, it's not so easy to see, but over long time scales, there will be an accumulation of anions. So these are the green spheres on the left, accumulations of cations on the right. And at the bottom, the second movie was showing how the charge fluctuates inside the electrode. So you see that when we have a red region, it means that we have accumulated some positive charge. On the contrary, green region means accumulated negative charge. And so progressively, we will charge these electrodes. So this is really consistent with what is done in experiments. And so does this simulation setup work well? To check this, we compared a system with some experiments. And so the main quantity which is measured is the amount of charge per gram of carbon, and this is obtained through cyclic voltammetry, as you have an example here on the left. And the typical value which is obtained in experiment is about 85 farads per gram for such systems. In our case, we have 110. So I think this is a good agreement. We have 20% of error at most. And so this means that we have the good concentration of ions inside the electrode. We have the good structure. And then we also checked the dynamics, because this is important since we are looking at power devices. And so for this, what we did is to compute the electrical conductivity of the liquid inside the pores. And this can be compared with some impedance measurements that were also made on the same systems. And here you see that the error is also of 25%, 80 instead of 60, that's on the right. So when we know the accuracy of classical molecular dynamics for transport in general, we can say that this is a good agreement, and so that the dynamics of the system is well reproduced. So then what we try to do first is to understand the effect of confinement. So what happens when you switch from a planar electrode like graphite towards a nanoporous one? And indeed, we observed similar effect as in experiments, because we had an increase of the capacitance by a factor of almost 2. So this can be made by, well, you need, of course, to normalize your results either using the mass or the surface. But in both cases, we see the same increase. And so we have something that is consistent with, again, with the experiments. And the advantage, of course, of simulations of experiments is that we have access to microscopic information. And so in that case, what we showed is that, in fact, in this nanoporous carbon, the increase of capacitance is mostly due to the fact that you have some highly charged carbon atoms. And in fact, in graphite, we'll have a Gaussian distribution of charges, while when you start to go towards complex carbon structures, you start to have a very skewed distribution. And in fact, this corresponds to carbon, which will be only in contact with some anions or cations on both sides of the surface. And these are highly charged, and so you have a very strong effect of the confinement. This I will switch. And I think an interesting story about all this is that since the experiments in 2006 by the groups of Gogotsi and Simon, a lot of people have started to understand why these nanoporous carbons were giving increased capacitance. And I think this is a nice story about first a theoretical model, which was proposed by Kornishev in 2011. And in fact, it's a picture on the left here, in which it was his theory was that due to the screening by the pore walls and the fact that you have a strong confinement, you end up with a structure in which anions, for example, that normally would repel each other, so in the liquid you don't expect them to be in contact. Due to the screening, their Coulombic interaction is reduced, and so they are allowed to pack like this and to be in contact. And then, so our simulations were 1 year after, so we confirmed this by molecular simulations, because we saw the picture that you have here in the middle of ions that are packed together, either anions or cations. And it's only 5 years later that we could do some X-ray diffraction experiments. So these are the ones you have on the right. And in fact, if you look at the yellow region, this is anion-anion correlation. And what happens is that you have the blue signal, which starts to show some pre-peak at the bottom. And by doing reverse Monte Carlo, it was shown that this really corresponds to the superionic state first predicted by Kornishev. So I think this is a very good example of theory confirmed by simulation, then confirmed by experiments in order to interpret a physical result. Then we switched to more recently to the study of supercapacitors, because when you think of, we want a large surface area, we want carbon, we want confinement. So of course, people really quickly started to look at these systems. But of course, you cannot do this in normal graphene because you need to have diffusion inside the material. So the main experimental difficulty was to have some porous graphene, but this was quite overcome. But then a lot of the results were not as good as expected, because people were hoping that it would be a perfect material. So on our side, we did a simulation of this system, which is quite large even for classical simulation, because we have more than 40,000 electrode atoms, which have fluctuating charges. We have 5,000 ion pairs. So this required the use of supercomputers, of course. And we studied systems in which we have systematically varied the graphene interlayer from 7 to 10 angstrom. So the idea is again to understand in particular the effect of the confinement. And so what we observe is that when you change from 7 angstrom to 10 angstrom, you have a very large structural difference, because in one case, you can only accommodate one layer of ions in the middle of the pore. While when you have 10 angstrom, you start to have more space, of course. So it's not really a bilayer, because in fact ions are in a checkerboard, so they will not be in front of each other. They will alternate like this, but in the end they are widespread in a kind of bilayer inside the pore. And when we apply voltage, this does not really change. We enrich in cations or anions, but we keep this monolayer to bilayer. So what is the effect of this on the capacitance? Well, it has a strong impact because when you have the bilayer, you only have 60 farads per gram, while when you have the monolayer, you can go up to 100 farads per gram, so you increase by almost a factor 2 the capacitance. So this means that this monolayer is very important. When you look at the volumetric capacitance, it's even worse because, of course, you have the effect of the density that increases again the capacitance. But then what we observed is that the capacitance we get is lower than the one we had with the complex nanoporous carbons from before. And so this is a point I have put here. For the same ionic liquid, we have 100 farads per gram, while we could get 130 for a complex one. And so this was quite puzzling because we were expecting, as experimentalists, that the graphene would be a superior material, more because it has all the good characteristics. And so again, we try to understand at the microscopic scale what was the origin of this effect. And what we again did was to look at the charge per carbon atom. And here you have this distribution of this charge when you go from 7 to 10 angstrom. So this is orange, blue, green, and then red. And so you see that when you compare to the complex carbon, having the 7 angstrom pores means that you have carbons which are highly charged. So that's the red and the black tails on the right. So this is good for the capacitance. But in the 7 angstrom pore, you also have a tail on the left side. So you have some carbon atoms which have a strong negative charge. And this is something we do not see in the complex nanoporous carbon. And in fact, on the left, the complex nanoporous carbon has the same distribution as a 10 angstrom pores. And so what happens here is that, in fact, when you have a positive electrode, you want to accumulate anions, but you still have some cations. And in the 7 angstrom pores, they remain close to the surface, so they will induce a negative charge that is not good. While when you have the complex nanoporous structure, you allow them to go in the middle of the pore, so they are not in close contact with the electrode, and so they are not inducing this large charge on the surface. So in the end, it means that the nanoporous carbons, the complex ones, because they have some pore size distribution, they allow some good distribution of ions. So the ones that go close to the surface will go, the other go in the middle of the pores. So in the end, this is you have a synergistic effect between the small pores and the large ones. A last interesting effect that we have seen in this nanoporous graphene is that in fact we see some correlation between the various layers. So this is something that we first spotted by analyzing the trajectories like this. So you see in the blue rectangles that you have ions of the same charge that are facing each other. And so we try to characterize this further by computing some radial distribution functions. So what we do is that we project an ion from one layer to the other, and then we compute its distribution function with all the ions. And what we see is that we have this kind of funny correlation that so you have a peak for like anion and cation interactions at distance 0, because of course that's a projection which is in front of the underlying ion. When you have the 7 angstrom pore, you lose this when you have the 10 angstrom pore because of the bilayer arrangement. You don't have any more this. And if you don't polarize your surface, so that's at the bottom, if you don't have a constant potential algorithm to simulate your system, you completely lose this. And in fact, what happens is that when you absorb a charge on the carbon will have an opposite charge, and so it will attract again an opposite charge. So in the end, you have this kind of charge alternation, And so this is a kind of transparency of graphene, but linked only to the Coulombic interactions. So in conclusions, what all these simulations showed is that in the end, it's good to have some disordered carbons compared to graphene. So graphene is not an Eldorado for supercapacitors, unlike what we expected at the beginning. I did not show, but we also looked at the effect of the concentration of ions, but this is not very important for today. And I would like to finish with some acknowledgement. And so I would like to thank all the people who participated to this work. Now, as Laura said this morning, we are switching to more complex models. We are also trying to switch to polarizable models for the liquids. But for the moment, we are a lot in a development phase. So we are developing new methodologies. And I hope that in the future, we'll be able to simulate even more complex systems. And thank you for your attention.
Thank you very much, Mathieu. Again, another beautiful talk, impressive. So, are there questions from the audience? From the people can also write questions in the chat or raise your hand or just start to talk, but open your microphones. Otherwise, if there's some shyness, I can start to shoot first. Yes, my question is that yes, once again, I was trained, more transported, I would say, in the first wave of graphene Eldorado in the mid 2000 when graphene was discovered. There was a strong activity here, theoretical activity here in this lab, and then we said, okay, well, it's the Eldorado for electronic properties because of this and that, and there are now other 2D materials that are based conceptually on graphene, but they are look more promising. So again, here I mean, it's a perfect benchmark, but not the perfect material in real life. That's what we learned from this.
Well, we learned that in fact it's good to have defects in materials, and this is often the case when you look at batteries, when you look at many topics. In the end, having a perfect crystal is sometimes quite disappointing, and I think that's what occurring in that case as well.
So to be a bit more philosophical, a bit more focused on graphene. Yes. So another good point that comes out of this talk is that yeah, for us doing modeling, yes, of course, we need to start with the easiest, which in general the most perfect samples, and then we are always confronted at real life. In real life, for example, chemical reactions occur better on a surface, particularly on a defective surface, and so forth and so on. So, I mean, in your case, you use classical models already, even coarse-grained models, because, of course, given the huge scale of your simulations, that's the only way to do. And so, in a way, we are already up in the upper half of the scale towards the macroscopic work, and still you need to do something more. You need to include polarizability. So, what's your take? We discussed a lot these days that we have, let's say, quantum calculations and our difficulty to scale up a little bit. My feeling is that you are in between. You are still doing atomistic or almost atomistic calculation, but sometimes you need to scale down and go down. So what's your take on that?
Well, my take is that what I'm saying now is that a lot of people have developed tools that will be very efficient in the future, and I think that's what a bit Rodolphe was saying before. We used to have methods and codes that were very highly separated, and you could not mix easily two methods. But I think that now, for example, I saw it when and especially thanks to Laura who spoke this morning, She tried to make our molecular dynamics code much more flexible in a way that it can be called using Python scripts, for example. And I think a lot of codes are now doing this. And I think in the future, mixing several methods and several scale will be more and more doable. So my take is that we will need all these. We won't have a simple model that includes everything and is fast. That will not. Well, there is no free lunch as usual, but we will be able to have some multi-scale simulations made efficient, while in the past I think it was very difficult to do this.
Okay, thank you. I agree, but yes, it's pretty much what also we were saying in the end of previous talk. Yes, we're going towards, I can easily see that in 10 years from now, possibly less, everything will be, all these codes and stuff will be easily interfaced with one another. So codes means methods and scales. Other questions from the audience? Or for written or oral? Well, if not, I will thank Mathieu again, and actually will thank all the speakers from this morning session. Of course, you notice that they were all from Sorbonne University, because again, with in SU, in Sorbonne University, we have this culture now since a few years, for 10 years, of strong interaction between people from the physics and the chemistry community in simulations. And I said that several times. And so this multi-scale vision of our calculation, what we need to do or what we want to do to be better, to have more predictive and more quantitative results, is really at the heart of our collaboration here. So yes, ideally, again, once again, we should be able in the near future, hopefully near future, to join together everything you saw in the last 3 days. So that's the goal for 21st century computational material science, is to really take everything from the quantum nature of the particles, of the electrons, to the almost mesoscale simulations that Mathieu, for example, just showed us. Okay, I think it's time to wrap up.
Yeah.
I see that Christian has also switched on his mic. So please, I've spoken a lot this morning, so it's time to do this.
Okay, I can just repeat what you said. Okay, it was, I mean, unfortunate that we had this coronavirus crisis, because we would have loved welcoming all the people here in Singapore and then have a very enjoyable week. First, I mean, learning new techniques, and also all the discussions around, and of course also visiting Singapore at the same time. Okay, so we have decided, I mean, to keep the same period of the year for some organizational reasons. So we will have to wait for 1 year before, I mean, being able to welcome you for good. Hopefully, I mean, coronavirus will be gone, and no other kind of devious, I mean, virus will be on the market. Okay, so so we will keep you tuned for all the people who registered. Okay, and we will make announcements of course, and if we organize any kind of workshop or conference around this high performance computing, we will also let you know. Okay. So I thank also all the lecturers for the good lecture. As it was just a teaser, of course. I mean, the school that we will organize will be different. Marco, I mean, maybe you want to repeat what you said earlier, and we want to also thank all the people who helped. Okay, having, I mean, this successful, I mean, workshop. and that would be helping us for setting up the school next week. I'm thinking of course, of Yvonne, okay, who was very key in organizing all of that, and also Cassandra, okay, who was helping during this this week, okay. So
yes. I really want to join Christian in thanking Yvonne, because throughout these long months, even when we were still hoping to do the school for real, she was the constant presence, and also the constant reminders to us, the organizer, that we needed to do some work to be able to organize. So it was really very, very helpful and very safety for us to know that Yvonne was always on top of the calendar of all the many things to do, even when the school was canceled and replaced by an online event. So that was a great job. And also Cassandra did a great job all these days in handling all this live Zoom platform. So thanks to both of them. Thanks, of course, to the other co-organizers, Dario Poletti and Kwek Leon Chun, that also were very important in building the program. As you can see, as you could see, the program was spent still a wide variety of people, of communities. Even if seen from far, seen from experimentalists, we do the same things, but we don't. We will do. We are, as I said before, we will hopefully do something in the future. And I don't know. I think that's it.
Yeah, I just would like to add something, I mean, which is
Yes.
more in tune with, I mean, this kind of workshop, okay, is that, of course, HPC, and in particular with material science, and also with quantum objective or not, but whatever, okay, is very important in Singapore. So, I mean, of course, I mean, we know that, you may know that we have this CNRS structure Majulab, okay. We have also, CNRS also other, what we call international joint units, okay. Sintra, who is doing more engineering science, for example. We have also another UMI, which is IPAL, which is doing more artificial intelligence, and another one on mechanobiology. So I mean, I'm sure that there is room for collaboration in Singapore. Would you be interested? So of course, I mean, coming year, next year could be, I mean, a way for you to meet with the local researchers and maybe try to start anything. But of course, if you have questions, you can contact me and I will be happy to help. I also must say that in Sorbonne University, we have a mirror site for Majulab, and Paul Indelicato, you may know, is the director, but I know that also Marco is strongly involved in that, because it will be part of the Majulab community. Okay, so of course, feel free also to contact Marco, and he will liaise with me and so on. Okay.
Okay, I think we said everything. So thanks to all the participants. I mean, you were numerous these 3 days. Considering it's being available for 3 mornings in France and 3 afternoons in Singapore all day long is not an easy task. That's also why conferences and schools are good, because when you move to somewhere else, you are focused on the conference or the workshop, the school. If you don't move, you are still trapped with all your day-to-day occupations. So that's very important. That's very nice that you have been with us so this long. So I think that's it. Hopefully we will meet in person next year. So enjoy the rest of the week. Let's stay focused on getting out of this coronavirus crisis, and see you next year.
See you next year, or before. Okay.
Bye-bye.
Bye.
Bye.
Bye.